Hello everyone, welcome to my video on the second derivative test, or SDT. So in the previous video we saw the first derivative test, and the first derivative test gave us information on the original function, namely whether the function increases or decreases. Well, what does the second derivative test give us? It gives us something called concavity. So let's go ahead and look at the definition of concavity. So if the graph of f lies above its tangents, then we see that the function is concave up. If the graph of the function f lies below all its tangents, then we say that the function is concave down. So let's look at a sketch to see what we're talking about here. So if I consider the sketch here, this is the x-axis, y, and I like to draw quadratic, so let's go ahead and draw a quadratic function. I have something like this. Well, let's analyze all its tangents. If I take the tangent over here at the bottom, we have something like this. If I take the tangent at this point, it's going to look something like this. And if I take the tangent at this point, it's going to look something like this. Notice that the green function is always above all the tangents. This means that this function here is concave up. Namely, if we draw, similarly, if we draw the function in the reverse direction, something like this, we see that the tangents are always above the function. So if I take the point here, something like this, the point here, the tangent looks like this. So notice that this function here, the green function, always lies below all the tangents. That means this one here is concave down. So this is an example of a function which is concave up. And this is an example of a function which is concave down. Okay, let's keep going. So here we have two important statements. First, if f double prime of x is greater than 0, then f of x is concave up. Namely, if the second derivative is positive, then the original function is concave upwards. Second, if the second derivative is negative, f double prime of x is less than 0, then f of x is concave up. Okay, so I'm not going to prove this. It requires the mean value theorem, which we haven't seen yet. But just to have a visual, a way to remember this is if the second derivative here is positive, you could think of someone being positive, a positive person, are more likely to smile. So this looks like a smile. So it's concave up, it's opening upwards. Okay. Whereas a negative person is more likely to be frowning. So here we have like a sad face. So the second derivative is concave down, it's opening downwards. This is what the function looks like. So here we introduce a new term that we have to know. So for first derivative test, we use this term called the critical point or the critical values. Now for second derivative test, we use this term called the inflection point. So by definition, the inflection point occurs where the function changes concavity. Okay. So another way of thinking of it is it's the point c comma f of c where the second derivative equals 0 or the second derivative does not exist. So the image that you should have in mind, if you're given a function, this is a function in green, the inflection point occurs when, notice the first part of it is concave up, the second part here is concave down. So at this point here, that's when the concavity changes. So when it changes from concave up to concave down, that's when we have an inflection point. But it could also change from when it's concave down to concave up. So that point where it changes concavity, that's where we have an inflection point. So this leads us into the second derivative test. So what it states is that suppose f double prime of c is continuous for x in the neighborhood of c, so it's continuous for all x values close to c. Then we have our first case. Case 1 is the local minimum. So f of c has a local minimum at c if f double prime of c is greater than 0 and f prime of c equals 0. Namely, what we're saying is that the second derivative is positive, so it's concave up, and f prime of c equals 0, so it has a horizontal tangent at c. Okay, the slope of the tangent is 0. So I drew a sketch over here. We have, let's say, a quadratic function. It's concave up, it's positive, f double prime of c is positive. And we have, at the value c over here, we have our horizontal tangent, so f prime of c is 0. What can we state about this value here? Well, if these two things here occur, then we know that this value is a local minimum. Okay, so horizontal tangent at c and its second derivative is positive. This means that at c we have a local min. So similarly, case 2, we have a local maximum. F of c has a local maximum at c if the second derivative is negative and if f prime of c equals 0. So the second derivative is negative, means it's concave down. So our original function here, f of x, is concave down, and f prime of c equals 0, so we have a horizontal tangent at c. So at this point here, that means that if we have both these conditions, then this point here has to be a relative or a local maximum. Okay, so concave down and horizontal tangent gives us local max. Okay, so this is what the second derivative test tells us. So here we have the strategy for solving second derivative test problems. So step 1, we find the inflection points. How? By setting the second derivative equal to 0. You set the second derivative equal to 0, solve for the value of c's, and those are the x values corresponding to the inflection points. Once you find those x values, what you're going to do is you're going to test values to the left and to the right of the value c that you got in part 1. Once you found your test values, take them and substitute them into the second derivative, because remember, we're doing the second derivative test, so your test values get plugged into the second derivative test, or the second derivative function, sorry, not the original function, so don't make that mistake. So we substitute our test values into the second derivative to see if the values are positive or negative. Once we do that, we determine whether we have a function which is concave up or concave down. If it's positive, it's concave up. If it's negative, it's concave down. So in this first example over here, it's asking us to find the inflection points of the following function. F of x equals x squared times e to the 4x. So let's go ahead and solve that. So to find the inflection point, we're just taking the second derivative and setting the function equal to 0. So let's go ahead and start. So the first derivative, f prime of x, is equal to, what you have to catch here is that we have a multiplication of two functions, so we're using product rule, f times g prime. It's the derivative of the first times the second plus the derivative of the second times the first. So the first function, the derivative is 2x. We leave the second function, e to the 4x, plus derivative of the second function is e to the 4x times 4, so we're applying chain rule, and then we're going to multiply by the first function. Okay, let's go ahead and simplify. We can express this as 2x e to the 4x plus 4x squared e to the 4x. So that's the first derivative. Let's go ahead and find the second derivative. So we're going to take the derivative once more. So f double prime of x. We're going to start off with the first term. Here we have a multiplication again, so we have to use product rule in here. So what we get here is, this is my first function, this is my second function. So the derivative of 2x is 2 times e to the 4x, plus the derivative of e to the 4x is e to the 4x times 4 times our original 2x. So that was the derivative of these two functions here, the multiplication of these two functions. So this part's done. Let's go ahead and do the same thing here. So again, it's a multiplication. My first function is 4x squared, so I'm going to take the derivative of 4x squared, giving me 8x times e to the 4x, plus, because we're doing product rule again, the derivative of e to the 4x is e to the 4x times 4 times the original function, 4x squared. Simplifying all this, we get, let's see here, we get 2e to the 4x plus, here it's 8x e to the 4x, and here it's 8x e to the 4x, giving us 16x to the times e to the 4x. And then lastly, we have 4 times 4 is 16 plus 16x squared e to the 4x. So what we could do now is factor. If we factor this out, we get a 2 that comes out. They're all even, the coefficients, so we could factor out a 2. We can't factor out an x, he doesn't have an x, and we could factor out e to the 4x. So 2e to the 4x, leaving us with 1 plus 8x plus 8x squared. Okay, could we factor this? So we're setting this equal to 0. We took the second derivative, we want to see if this is equal to 0. Factoring out this, what do we get? We get so it's product rule. sorry, not product sum, two numbers that multiply to give us 8 and the same two numbers that add to give us 8. So this won't work. So we can't use product sum here, so we have to resort to our backup. Our backup is quadratic formula. So let's go ahead and do that. So let's go ahead and solve this using the quadratic formula. The quadratic formula is x12 minus b plus minus the square root of b squared minus 4ac over 2a. So the b in this case is 8, so minus 8 plus minus the square root of 8 squared minus 4ac. 4 times a, which is 8, and c is 1. All this divided by 2 times a, 2 times 8, giving us negative 8 plus minus the square root of 8 times 8 is 64, minus 4 times 8 is 32, over 16. Minus 8 plus minus the square root of 32 over 16. 32 could be written as 4 times or 16 times 2. And now we can take the square root of 16 and leave out the 2. So this is really negative 8 plus minus the square root of 16 is 4. The 2 is still trapped inside the root, so we get 4 root 2 over 16. And now we could simplify both terms, giving us negative 1/2 plus minus 4 over 16 is a quarter with root 2 on top. So root 2 over 4. Okay. So those are the two values, which is going to let this equal to 0. Notice that we have e to the 4x equal to 0. Well, could an exponential be equal to 0? No, because we have an asymptote at 0. So exponentials can never be equal to 0. There's no value that you could put as x, replace x with, to make it equal to 0. So this can't be equal to 0, the 2 can't be equal to 0, so the only way for this to be possible is if x equals x1 or 2 equals this. So we have two inflection points. We have negative 1/2 plus square root of 2 over 4, and we have negative 1/2 minus square root of 2 over 4. So those are the x values. To find the points, what we have to do is just take this value and substitute it back into here. So remember, when you're looking for an inflection point, it's a point. It's an x and y value. Critical values are just one x values. Inflection points are the x value and the y value. So here we're not done. We have to find the point. So the point is for x1, negative 1/2 plus root 2 over 4. Plugging that into here, we get, let's just leave it as is, negative 1/2 plus square root of 2 over 4, all that squared, times e to the 4, negative 1/2. Well, if we multiply this in by 4, we get negative 2 plus root 2. Okay. That's the first inflection point. And then the second one, when we do the minus, we have negative 1/2 minus root 2 and 4, comma, negative 1/2 minus root 2 over 4, all this squared, times e to the 4 times x, so 4 times this thing, giving us negative 2 minus root 2 in the exponent. And these are the 2 points. These are 2 inflection points. Okay. So this is the idea. Usually it's numbers that work, but here you could plug this into your calculator. If you don't have a calculator, you would express your answer in this method. Okay. So in this example here, it's saying to use SDT, the second derivative test, to determine the interval for which the function f of x equals 2x to the 5 minus 5 over 2x squared is concave up or concave down. So we're using the second derivative test. Let's go ahead and begin by taking the second derivative. So we have to start off by taking the first derivative of the function. The function here is continuous. It's a polynomial, so we're okay with that. Taking the derivative, we get 10x to the 4 minus 5x. Okay, that's the first derivative. Let's take the second derivative because we're looking for our inflection point. The second derivative is 40x cubed minus 5, and this is equal to 0. Now let's go ahead and solve for x. We can bring the negative 5 over, we get 40x cubed equals positive 5. Dividing both sides by 40, we get x cubed equals 1/8. And the last step is we take the cube root on both sides. So what number could you multiply by itself 3 times to give you 8? Well, that's 2. So this is 1 over 2. So x equals 1 over 2. We found the x value of the inflection point. Let's keep going. So let's keep these two. Now let's create a number line. Negative infinity, positive infinity. The inflection point here is a half. And let's determine what's happening to the left and to the right of the inflection point. So let's test values to the left and right. And the values that I'll test are, to the left of a half is 0, and to the right of a half, I'll take 1. Okay. And we could create our little table of f double prime and f of x. So when we plug in 0 into the second derivative, we get 40 times 0 cubed minus 5, so 0 minus 5, we get a negative value. Okay. And when we plug in 1 into here, we get 40 times 1 minus 5, which is a positive value. So here we know that on this interval it's concave down, and here because it's positive, we know the original function is concave up. And that's the idea. And that's the answer. So to answer the question, we have concave up. I'm going to use CU, abbreviated. It's concave up on the interval from 1/2 to infinity, and it's concave down, which I'll abbreviate CD, from negative infinity to 1/2. And that's the answer. Okay. So in this example over here, it's asking us to determine the interval of concavity and to find the inflection points, if they exist, of the function x to the 4 minus 8x squared plus 6. So let's go ahead and do that. Step 1, let's go find our inflection points by taking the derivative of this function twice. So notice that the function here is continuous. We're dealing with a polynomial function, so we're okay. We begin by taking the first derivative. So the first derivative of this is 4x cubed minus 16x, and that's it. Taking the second derivative, f double prime of x, gives us 12x squared minus 16. Okay. So we take the second derivative, set it equal to 0. What we could do here is factor out of 4, leaving us with 3x squared minus 4 equals 0. Now we can use a zero product law. You can use difference of squares here, but I think zero product law is the way to go. Or divide both sides by 4. That's another way. So if we divide both sides by 4, we get 3x squared minus 4 equals 0. Bring the 4 over, we get 3x squared equals positive 4. And now divide both sides by 3, giving us x squared equals 4/3. Now we can take the square root on both sides, and we get x equals plus minus 2 over root 3. So those are the two values. Let's rewrite that. 2 over square root of 3. So we have two inflection points. Positive 2 over root 3 and negative 2 over root 3. Okay. So let's go ahead and draw a number line. So we have negative 2 over root 3, and we have positive 2 over root 3. Okay. And we're going to test values. Let's use a calculator to see what the actual value is. This is about negative 1.15. And this is positive 1.15 about. So the test values, we have to choose values in between, which is easy. One's negative, one's positive, so we could just take 0. To the left of negative 1.15, we could take negative 2. and to the right we could take positive 2. So we're going to take the test values and plug them into the second derivative. We're working with concavity here. We're using the second derivative test. So let's box our inflection points in. Or I shouldn't say inflection points, it's our potential inflection points, because we don't know if these are in fact inflection points, because remember, we need a change in concavity. So one has to be positive, one has to be negative. If we get two positive values next to each other, this is no longer an inflection point. So if we have the second derivative and the original function, so when we plug in negative 2 into the second derivative, we get f double prime of negative 2. That gives us 12 times negative 2 squared minus 16. 12 times negative 2 squared is 4, so 4 times 12 is 48 minus 16. And we get 32, positive 32. So the fact that it's 32, we don't really care. We care about the fact that it's positive. So this value is positive, we're done. Let's check 0. When you plug in 0 into here, you get 12 times 0 squared, which is 0 minus 16, so you get a negative value. And then when you plug in 2, you get essentially the same answer as over here, because positive 2 squared times 12 is 48, minus 16, we get 32, so this is going to be positive as well. Okay, so what can we conclude about negative 2 over root 3 and positive 2 over root 3? Well, first of all, since the second derivative is positive, we know the original function is concave up on this interval, and it's concave down on this interval, and then on this interval here, it's going to be concave up. Okay. So this means that since there's a change in signs, this is in fact an inflection point. And same here. Since it went from negative to positive, this is in fact an inflection point. Okay. So to answer the question, we have two inflection points, one at negative 2 over root 3 and positive 2 over root 3. Now to find the point, we're just essentially going to plug these back into the original function. Okay, so to get the actual point, you just have to plug this back into the original. And now to answer the question of the interval of concavity, well, let's write this down. Let's erase this. So let's write concave up as Cu. When is it concave up? Well, it's concave up on the interval from, this is our number line. It goes from negative infinity to positive infinity. So it's on this interval here to the left of this point, which is negative infinity to negative 2 over root 3. And then it's concave up again after this value. So union 2 over root 3 to infinity. Okay, so this is when it's concave up. To find concave down, it's essentially the rest. So concave down, CD. It's on the interval from negative 2 over root 3, union, oh sorry, that's not, no union. There's only one instance where it's negative, so it's between negative 2 over 3 and positive 2 over root 3. Okay, and that's the interval of concavity.